So I'm back, this time for part of Preliminaries 1.2 Sets and Equivalence Relations. So the set theory, I know you have passed this subject last summer, and I'm sure with those experience and the videos you have watched last week, you have already maybe stronger background with set theory. So let's begin with the term set. So I will not be discussing this one, but we'll go over the terms that are probably new to us all. So set is common. It is a well-defined collection of objects. That is, it is defined in such a manner that we can determine for any given object X whether or not X belong to the set. That means when we mean set, it should be well-defined. When we say well-defined, we know that there are or there is a certain object that really belong to that set. Okay? We call elements or members those things or objects that belong to the set. We have also the notation. This one, we use this to mean as element of something, an object. N, natural, group of natural number. Z, group of integers. So these are more important sets that we need to consider. Okay, Q for rational, R for real, C is for complex numbers. So these are common sets of numbers. Okay, we have also various relations between sets and can perform operations on set. A set A is a subset of B. Okay, written A subset of B or B subset of A. Or A, yeah, subset of B, if every element of A is also an element of B. For example, this one. And so, the relationship between these sets of numbers are N is a subset of Z, Z is a subset of Q, Q is a subset of R, and R is a subset of C. Therefore, the highest among them is the complex numbers because complex numbers caters real numbers, and under real numbers we can have rational, we have integers, and from integers we can get the counting numbers. Okay, and then you have also proper subset. If a set is a subset, is not a subset of itself. Okay, so proper subset is of a set A if B is a subset of A but B is not equal to A. So there's uh, a set is a subset of itself, but we cannot call it a proper subset if it is true that that A is a subset of B and they are equal. So that is not a proper subset. When can we say that two sets are equal? If we can show that A can be a subset of B and B is a subset of A. So it is convenient to have a set with no elements and it is called empty set. You know that. We can denote empty set by this figure. Note that the empty set is a subset of every set. So to construct new sets out of old sets, we can perform certain operations of sets. What are these? Union and intersection. Okay, we have also disjoint. If two sets don't have common elements, they said to be disjoint. We have universal set. Universal set. We have also complement. Okay, complement is not in, yeah. And we have also difference of two sets. And here are example here. Let the real numbers be the universal set and suppose that A is equal to X, element of real numbers such that X is less than or equal to 3. and greater than 0. So what are the elements of this set? Okay, that is 1, 2, and 3. How about this one? B. B equals x, element of real numbers such that x is greater than or equal to 2 but less than 4. That means that is only 2 and 3. Then perform this operations. Say, I would like to remind you that you should be able to read, notations like this. Okay? And of course, if you can read and understand how it is written, hopefully you can write sets in this form, set builder form. Okay, there are proposition here, proposition 1.1. And then we have proof, we have theorem, De Morgan's laws, let A and B be sets, then the complement of A union B is the complement of A intersection B prime. So there's also a proof for that. And then example 2, Cartesian products and mappings. We have also discussed that. Cartesian product A cross B. And then relations, mapping or function of F, domain, and then range or image. What else? Here's an example. A well-defined relation, onto or surjective, one-to-one or injective, and both one-to-one and onto is called bijective. Okay, we have passed through that. We have also composition of functions. I hope you can remember this. A composition of function is another way to work with functions, and the value of x or the input of the function is a function. That is a composition of function. Okay, like this. G circle f of x is equal to g f of x. Notice that's supposed to be G's input is another value, g of x. And the x now is the f of x. That means a function is the input of another function. So whatever the value that we can get from that function can also be the input to the outside function. Can you understand? Do you understand what I'm saying? Hopefully, composition of maps. And then what else? Matrix, okay, linear maps or linear transformations. We will go back to that next time. What else? Permutation and identity mapping, inverse mapping, invertible. Did I include all this in the video presentation? This is part of sets, and mapping is invertible. Anyway, I would let you watch most of those. So equivalence relations and partitions are discussed today, and these are the properties: reflexive, symmetric, and transitive. We have also examples here. Okay, partition P, similar equivalence classes of X, and then what still? Equivalence classes. You have watched it in the video presentation. Congruent to S modulo N. So we will be dealing with modulo N maybe next week. And then here are some exercises that I might give you on Thursday. Okay. So let's proceed with the integers. Integers. We have mathematical induction, which is, I think, we'll discuss in that presentation, but you can visit this one. This book, you can upload this from the internet, the first principle of mathematical induction and the second principle of mathematical induction. I hope you got the presentation. The principle of well ordering, because we need this principle to prove mathematical induction. What else? The division algorithm, of course, is very common, and you can still meet this in your um, another subject on polynomials. I forgot the title. So division algorithm, common divisor, greatest common divisor, relatively prime, and the Euclidean algorithm, prime numbers, fundamental theorem of arithmetic, and historical note, and we're done. That means tomorrow, or yeah, tomorrow. This day, I'll be showing this presentation to you. I'll be uploading this, and then tomorrow I will add up another video presentation that will help you really understood the division algorithm part of this book. So that's all for this presentation. Thank you very much. If you have questions, don't forget to ask and to send it through Canvas inbox or private message.